rest of your day. 85. Okay. Huh? 52? Okay, cool. Okay, which number?
52.
52? Oh, it's up there already.
Oh.
We're good.
Oh, and also 63.
63? Hi. 105?
73 and 78.
73 and 78? We did 73. Oh, 73 is done already, and 78 is done already. Those were done on the video. Okay? Alrighty. We need to turn that thing on. Go. Is it warm in here today? Like, I dressed warmer today because I was so cold yesterday, and now I'm like, oh. Yeah, and I'm wearing like 2 pairs of socks with my boots because my feet were freezing yesterday, and I wore a long sleeve shirt that's a little bit thicker, and I'm like, I'm way too hot now. I just can't win. It's freezing yesterday, wearing my bloody parka. Anyway, all right. We do not want electrochemical cells. That's my AP class. Oh, it's not plugged in, right? Thank you. Okay. Okay, so we are going to start with number 52 and work our way up, I think. Oh my God. Okay, I can't deal with that. There we go. Okay. Number 52. In an experiment, a student mixes 0.2 molar lead with 0.4 molar iodide. So Q, because it's PbI2, it will dissociate into Pb plus, Pb2 plus 2I minus. And so Q is going to be equal to Pb2 plus, oh, what am I doing? Sorry, brain in a little bit of a, there we go, that's better. Pb2 plus times I minus squared. So all you do is you stick the lead concentration where it says lead, 0.002, and you stick the iodide concentration where it says I, 0.004 squared, and we get whatever it is that we get. 0.002 times 0.004 squared is 3.2 times 10 to the negative 8. Do not double the iodide. The concentration of iodide is 0.004. Yes, that's what it says. It's not 0.008 because otherwise it would say the concentration of iodide is 0.008. Okay, all right. 52. What's next? We got 61 and 63. 61. We want AgCl to be the most soluble. So which way do we want this equilibrium shifted? We want it shifted to the right. So if we were to add HCl, that would be adding H plus ions and Cl minus ions. Uh-oh, that would shift it the wrong way. Yes? Oh, look, MgCl2 would produce Mg and Cl, which would cause Cl to go up, which would cause it to shift the wrong way. AgNO3 would produce Ag plus and NO3 minus, which would make Ag plus go up, which would cause it to shift the wrong way. And NH4NO3 actually doesn't react with anything. But seeing as the other three make it less soluble, there's nothing to shift it to the right. So just its normal solubility is the most soluble. Yeah? 61, 63. There's a problem with this question. This should say 0.25 moles. Does that fix it? Probably. Yes? So I'm just going to leave that one because I think the problem is it should not be 25 moles, otherwise the question makes no sense. Did anyone want me to go through it anyway? No. Okay. 63. Stab myself in the eye. 69. Which of the following solutes has the highest solubility? Take a look at those anions. You've got silver, 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 silver. Which anion is soluble with everything? Nitrate is soluble with everything, so that's going to have the highest solubility. All the rest of them are going to be low thingy salts. Low solubility salts. 84. Did I do a 63? I think I did. Yeah, I did. That was the one that was just wrong. Okay. 84 and 85. This is a bad question because there's two possible correct answers. Okay, so let's just get rid of this one as an option because it is the second correct answer. So the question is a bad question. Yes? If I get rid of that one, which would cause more of the solid to dissolve? Well, it can't be CO3, right? Because that would cause it to shift to the left. It can't be MgCO3 because that is a low solubility salt. And whatever did dissolve would cause it to shift to the left, but it would mostly just leave it unchanged. If we did add Mg could actually react with the CO3, producing MgCO3 solid, which would cause CO3 concentration to decrease, which would cause it to shift to the right. So that's why I said that is a possible correct answer, but the one I'm pretty sure that the question was actually looking for is the HCl, because when you have H, it can react with CO3 and produce H2CO3, which then further breaks down into H2O
and CO2. So you get bubbles forming, okay? I would not give you that one on the test because it's a bad question, obviously. 85. The equilibrium in a saturated solution of lead oxalate is shown. We add some sodium oxalate is added to a saturated solution. So we have increased the concentration of C2O4. So the system shifts to the left. And if it's shifting to the left, what has happened to the solubility? Anytime we shift towards the solid, the solubility has decreased. Yeah. 85. Oh, we just did 85. 94. I'm just going to take a quick stop by question 90 because question 90 is unanswerable. Just cross it out. Okay? It does not have a correct answer. Bad question. Number 94. What is the maximum number of moles that can exist in 500 milliliters of 2 molar AgNO3? And what that means is that without a precipitate forming, yes? So that's a maximum. So that's going to be the case where you have your KSP and it's going to be for AgBr. That's going to be our solid if we're identifying the precipitate. The precipitate is AgBr. And so KSP then is equal to the concentration of Ag times the concentration of Br minus. We know the concentration of silver, yes? We also know that the KSP is given in the data booklet. And if that's the case, we just take those two variables, plug them in there, and solve for Br. So let's go look up our KSP value for lead bromide. No, silver bromide. 5.4 times 10 to the negative 13. .4 times 10 to the negative 13 is equal to 2 molar Ag times the concentration of Br minus. So the concentration of Br minus then will be 5.4 times 10 to the negative 13. Excuse me. Oh dear. Okay. Divided by 2.0. And we get 5.4 E13 negative divided by 2 is 2.7 times 10 to the negative 13. B. Where are we? 105. Calculate the concentration in molar of iodide ions in a saturated solution of lead iodide. Yes. 94. Sorry. Oh, yeah, because I was leaving it as molarity, but we want the number of moles, not the molarity. And look at that, they tricked me. Oh. Okay, so that's our molarity. That is our moles per liter. And we have half a liter, 0.5 liters. Thank you for catching that. 2.7 E13 negative times 0.5 is 1.35 times 10 to the negative 13. So that should be A, not B. Yep. Yes. Yes, of course. 105. So we want the concentration of iodide in a saturated solution. Since it doesn't give us any of the concentrations, we have to assume that this is a dump and stir situation. Otherwise, they would have had to have given us some concentrations of either ions or compounds. So we have lead iodide at PbI2 in equilibrium with Pb2 plus 2I minus. And if our solubility is X, then this is X and this is 2X. And so then we would solve, and this is one of the cases where you could use the shortcut. We have an AB2 compound. KSP then is equal to what? By the shortcut. 4x cubed. If you don't know that, you can go through the whole process and say KSP is equal to lead times iodide squared, which is equal to X, times 2X squared, which is equal to X, times 4X squared, which is equal to 4X cubed, which is what you would want to do if you were doing a written response question to show that you can derive it. But on multiple choice, you can go straight to here as long as you know that. Okay, saves you a little time. So then x cubed is equal to 4 over the KSP, which is equal to 4 divided by 1.39 times 10 to the minus 8. Woo! And that is, did I do that right? 4, no, I did not. It's divided by 4. It's KSP divided by 4. Silly me. KSP divided by 4. Ay, ay, ay. All right, so we have 1.39 times 10 to the minus 8 divided by 4. I got a huge number, which let me think, oh, something's wrong with my answer. 1.39 times 10 to the minus 4 divided by 4 equals times 1 times 10 to the minus 4 because I put it to the wrong power. Okay, so that is 3.48 times 10 to the negative 9, and that is equal to x cubed. We do not want x cubed, we want the concentration of I, which is 2x. So first we need to find x, so that will be the cube root of 3.48 times 10 to the minus 9, which is 1.5 times 10 to the minus 3, and then 2x, which is the concentration of I, is going to be 3.0 times 10 to the minus 3. And there we are. Hopefully that's an answer. 105, 3.9, 5 times 10 to the minus, what? 3.0 times 10 to the minus 3. Ah, that looks good. There we are. Yeah? Somebody wanted like 78. Let's just go take a look there because what the heck, we got another couple minutes. Might as well. 78. Did we want 72 or 73? No? Okay. 78. 72, yes. Which of the following saturated solutions has the lowest concentration of carbonate? So for this one, you are going to be looking at certainly not ammonium, because ammonium is soluble with everything, yes? And therefore it will have a high concentration of carbonate. The other three, magnesium, calcium, strontium, are all low solubility. If you check on your data booklet here, you will see that carbonate, magnesium, calcium, and strontium, they're not alkali ions, so they are part of the low solubility. So to tell the difference between them, you would need to carry on to page 5, and you would see that magnesium carbonate has a power of 10 to the negative 6, yes? Whereas strontium carbonate, strontium, has a power of 10 to the negative 10 for its KSP. Out of those two, which one is less soluble, which would have a lower concentration? The strontium, yes? And we can then compare with our final one, which is the calcium, but calcium is -9, so again, that's higher solubility than the strontium. Any others that anyone would desperately like? We're okay? All right. So let us do acids and bases then, shall we? Yes? Back to 4.1 F. So remember a Bronsted-Lowry acid? What do Bronsted-Lowry acids do? They give a proton away. Bronsted-Lowry acids give a proton away. Bronsted-Lowry bases do what? They take a proton. And someone asked me yesterday, so I just wanted to quickly put this in here. How is it, say for example, how does a Bronsted-Lowry base make hydroxide? Because I didn't put it in here because it was in the other notes, but I just wanted to make sure there was clarification on this because it is important. So for example, NH3. If we look on our data booklet, acids and bases, page 6, and we look for NH3, here it is right here. It's on the right-hand side. What kind of substances are on the right-hand side of this chart? Look up at the top. What are they? They are bases. Okay, so what that means is that ammonia is a base. It's in the white area, not the gray area. So is it a strong base or is it a weak base? It is a weak base. Okay. Now, just because we're talking about ammonia, I also wanted just to take a look here. Ammonia also appears on the left-hand side, which would imply that it is what are on the left-hand side? acid. So we look up and we're like, oh, acid. However, what do you notice about this arrow? That arrow goes one way. Is NH3 able to give away a proton? No, otherwise that would be a two-way arrow and it would show it being able to go in the right-hand direction, okay? So ammonia is not an acid. Because it is too weak to act as an acid. But how on earth, how on earth does ammonia, NH3, end up giving us a basic solution? Basic solutions contain hydroxide. Yes? NH3 doesn't have any oxygen in it. So how are we getting that hydroxide? Well, if we have an aqueous solution of NH3, what else is present in the beaker? Water. And if NH3 acts as a Bronsted-Lowry base, what does that mean that water will be acting as? What is a Bronsted-Lowry base? It is a proton acceptor. Which means, what's a proton? Hydrogen. If it is going to accept a proton, where will that proton come from? It's going to come from water, which makes water what kind of a substance? A Bronsted-Lowry acid. Yes? Anytime you have a Bronsted-Lowry base, there must be something else acting as a Bronsted-Lowry acid. Otherwise, who's going to be giving it the proton? There has to be somebody giving the proton, right? So we have water, and it is a proton donor here. So a hydrogen is being transferred from the water to the ammonia. So ammonia is turning from a Bronsted-Lowry base into its conjugate acid. What is the conjugate acid of NH3? NH4 plus. Yes? Water acted as a Bronsted-Lowry acid. It's going to turn into its conjugate base. Yes? And what's left when it gives away its proton? Hydrogen and oxygen, which is OH minus. So how did this Bronsted-Lowry base make hydroxide? It took away hydrogen from water, okay? Behind. There we go. Now, while we're here and doing this, If this were going backwards, if this reaction were going backwards, so in the reverse direction, who would be the Bronsted-Lowry acid in the reverse direction, and who would be the Bronsted-Lowry base? Tell your partner. Oh yeah, for sure. Yeah, yeah. So if you don't want to write it down and just want to absorb it, that's totally fine. Yeah. In the reverse reaction, who's giving a proton to whom? NH4 is giving a proton to OH, which makes NH4 the Bronsted-Lowry what? Acid. And OH is the Bronsted-Lowry base. Yes? So in any equilibrium like this, you will always have a Bronsted-Lowry acid and a Bronsted-Lowry base on each side of the equation. Yes? Each side of a Bronsted-Lowry acid base equilibrium will have a Bronsted-Lowry acid and a Bronsted-Lowry base. Could you identify for me a Bronsted-Lowry acid-base pair? Do you guys know what that means yet? It's a Bronsted-Lowry acid-base pair is a Bronsted-Lowry acid and its conjugate base. The two species in a Bronsted-Lowry acid-base pair differ by a single proton. Yes, one of them has the proton, and then the other one doesn't. Yes? So if we were to go back then to our equation, and I'm going to just rewrite it down here. Who are the two conjugate acid-base pairs here? And remember, an acid-base pair, they differ by a single proton. NH3 and NH4, yep. And our second one is the H2O and the OH minus, yes? Are those terms starting to make a little more sense? They don't have to be perfect yet, but are they starting to make a little more sense? We're going to keep going with them, okay? Don't worry, we will keep explaining. Yes, of course. All right. I'll give you guys a minute to finish writing whatever you're writing, and then we will, don't forget I will post these, so don't worry if you didn't get a chance to write it all. And just to let you know, there's going to be a quiz on Bronsted-Lowry and strong acid and strong base and weak acid and weak base next Tuesday. Yay! Woo! Still trying to figure out how much of this course we're going to be able to cover by the end of January. And it's not even the end of January, it's like 3 weeks into January. So we may not get through electrochemistry. If you are planning on going to university and taking chemistry and you would like access to my electrochemistry unit, I've had my AP class self-study it. It's been mostly taught by Tyler DeWitt and Mr. Colger. Between the two of them, they do a pretty good job. I've got handouts that go with it, et cetera, et cetera. You're welcome to request a copy of that, okay? Because I'm not sure that we're going to actually get there. Alrighty? Okay. So back to, oh, there we go. There we are. Okay, and we were talking about amphiprotic substances last time. Remember, amphiprotic substances have to have a hydrogen in order to be able to donate a proton, and they must also have a negative charge to be able to accept a proton, or the only exception where they don't have a negative charge is water. Water is always amphiprotic. Okay. And we were looking at this table last day. And just to reiterate, up at the very top in that gray section on the left-hand side, we have our strong acids. If you have a color printer at home, I would probably print one of these myself if I had a color printer at home. Their conjugate bases are too weak to act as bases, and that's why all of our arrows on here are one way. Whoops, red is not a good color on there. ClO4 minus, for example, is not able to accept a proton and become HClO4. Once HClO4 gives up its proton, it is gone. Yes, it will not take it back. So HClO4 gets stuck in its conjugate base form, ClO4 minus. Yes? So we do still call ClO4 the conjugate base of ClO4, but it's just always stuck in that form, so it can't actually act as a base, okay? Up at the, you can see on the side here, we have these arrows where it says strength of acid here. And so even within the weak acids, we have weak acids which are stronger. A larger percent is going to be dissociated. Yes? So if we had our stronger weak acids, a larger percent of HA is dissociated into H plus and A minus. That is analogous, similar to solubility, yes? When something is more soluble, more of it is separated, yes? When we have the stronger weak acids, more of those acids are separated into H plus and A minus. Does that make sense? So it's kind of like but it's not solubility because the molecule itself is dissolved and floating around in the water, unlike the ionic crystal. Yes? But we do have more H plus and A minus dissociated. Down here are weaker weak acids. A smaller percent of HA is dissociated into H plus and A minus. So you'll have more of the HCN and less of the H plus and CN minus. Okay, and we'll actually do a K value with these, and we'll have the H plus times the CN minus over the HCN, because HCN is actually dissolved, so it has concentration, but we'll get there later. All righty. The base side is the exact opposite. It's upside down to the acid side. So your strong bases are right at the bottom. And I will let you know that people tend to get ammonia mixed up, and they see ammonia down in the gray section and they think, oh, ammonia, it is a strong base. What is wrong with that statement? Ammonia is a strong base. Why does that not work based on seeing it right here? Look at the reaction that's present in that line. It's a one-way arrow. Ammonia is not turning into anything else. And certainly, even if it was to go this way, what would it be doing if it went that way? Would it be acting as an acid or would it be acting as a base? If ammonia was able, which is not, to go this way, what would ammonia be acting as? It's giving up a proton, so it would be acting as an acid. But it's not acting as an acid because, why? Why is it not acting as an acid? It's too weak. Yes? Too weak. So ammonia is not a strong base. Who is the strong base? NH2 is the strong base. Okay? NH2 is the strong base. Here it is right here, and it's on the base side. This is on the acid side. These are extremely weak acids on the left and extremely strong bases on the right. The acid on the acid side in that gray box, they're too weak to act as acids, but in that gray box on the left-hand side, right-hand side, is that the right-hand side? Left, right. On the right-hand side, sorry, that just took me a minute there. On the right-hand side, those are our strong bases, and so they will accept protons and not give them back. Okay? All right, we will take a pause on the chart for now and come back and visit it again later. Okay, I'll give you guys a minute to write that down if you're writing it down. Anyone writing it down? No? Okay. I will post this as well, so if you missed it, don't worry. Okay, this just yaks about it a little bit more. You can feel free to read it if you want to. But we're going to look at example number 1. Is HSO4 amphiprotic? So let's consider our two equations. If HSO4 is acting as an acid, then it would be giving up a proton and becoming SO4 2 minus. And if we go to our data booklet and we look up HSO4, I think it's near the top here somewhere. HSO4, right here. Okay, highlighted. I'm going to zoom out so you can see where it is on your table. Okay, it's about 5 down from the gray zone. There's HSO4. What kind of a substance is HSO4 there? Is it an acid or is it a base? It's an acid. It's on the acid side. Is it a strong acid or is it a weak acid? It is a weak acid, but it is on the strong-ish side for a weak acid. I know these terms are stupid, but that's the best way that we can refer to them. It is a strong-ish weak acid because it's higher up on the chart. Now, can you find HSO4 anywhere else, HSO4 minus, anywhere else on this chart? Have your data booklet out or your purple sheet, okay, or your pink sheet, page 6. See if you can find HSO4 anywhere else. Yeah, it's on the top over here. Yes, we have HSO4 here. And that is in the base section, yes? So, is HSO4 able to act as a Bronsted-Lowry base? If it were anywhere else other than the gray zone, the answer would be yes. But in order for HSO4 to act as a base, this arrow would have to go that way as well. Yes? And it does not go that way. That means that HSO4 is unable to accept a proton. So HSO4 minus is actually an exception to the rule. Every other time you see a substance that contains a hydrogen and has a negative charge, it's going to be amphiprotic. Yes? Like if we go through and we look through anything else, oh look, here's HC2O4. Does my arrow allow it to be a base? Yes, it does. Yeah? How about HC2O4 as an acid? Let's go down our chart and see. Look, HC2O4. Does our arrow allow it to act as an acid? Yes, it does. Therefore, HC2O4 minus is amphiprotic. Yes? Let's find another one. Oh, look, here's another one. H2C6H5O7 has an H and it has a negative charge, yes? So here's its negative charge. Is it able to act as a base? It's on the base side. Does it have an arrow going in the base direction? Yes, it does. So it is able to act as a base. Let's see, can you find H2C6H5O7 on the left-hand side? There it is. Yeah. Is it able to act as an acid? Yes. In fact, any acid and any base that are within the white area, they are always able to act as either the acid if they're on the acid side or the base if they're on the base side. The only ones who are too wimpy, okay, are these ones here. These are too wimpy to be bases. And these guys down here, these are too wimpy to be acids. But everybody else can, if they're on the base side, they can be a base. If they're on the acid side, they can be an acid. Okay? So all of our substances that have a hydrogen and a negative charge, there's our hydrogen and our negative charge, hydrogen and our negative charge. H2CO2O4, we have our hydrogen and our negative. We have our hydrogen and our negative. That is amphiprotic because they can act both as acids and as bases. The only exception to that thing where you have a hydrogen and a negative charge is, get me a different color here, H2SO4. And why is that minus? Why is that not amphiprotic? It has a hydrogen and it has a negative charge. Why is it not amphiprotic? Yes. Because it is too weak to be a base. It is the only exception to that rule. Okay? So there we are. Where were we? Here we are. So equilibrium 1 does occur, so that's good. But this one does not occur because HSO4 is too weak to be a base. It's in the gray zone on the right-hand side. Okay. In order for a chemical to act as an acid, it must be mixed with a base. We've already talked about that. What if I take an amphiprotic substance like HCO3 minus? So I've got an H and I've got a minus, so therefore that is amphiprotic. How do I know what it is going to do? What do you think it will do when we put it with PO4 3-? Will it act as an acid or will it act as a base? Tell your partner. What do you guys think? Acid, base? Has to act as an acid. Who's it going to accept a proton from? No one. Nobody else has a proton. So it must act as an acid. PO4 minus can only accept protons. So if this is a base, then this must be the acid. Yes? And so what we're going to do then is we are going to transfer the hydrogen from the acid to the base. What will the products of this reaction be? Yeah, we're going to end up with CO3, 2-, having lost its hydrogen. And we're going to end up with HPO4. What's the charge of HPO4 going to be? It started out as 3-. Now it's going to be 2- because we put an H plus onto it. Yes, we added a positive charge as well as an H. Yeah? Okay, so here HCO3- acts as an acid because the PO4 is a base capable of accepting a proton. Label the Bronsted-Lowry acids and Bronsted-Lowry bases in the above reaction and identify the conjugate acid-base pairs. So we have the acid and base in the reactants. Who are the acid and base in the products for the reverse reaction? Tell your partner, who is the acid in the reverse reaction? Who is the base in the reverse reaction? Who's our acid in the reverse reaction? HPO4, it has to be, right? It's the only one that has a hydrogen. And an acid has to have a hydrogen to donate. CO3 does not have a hydrogen to donate. So this is our acid in the reverse direction. And that means that CO3 2- is the base. And if we were to identify our conjugate acid-base pairs, we're going to call HCO3 acid 1, and its base, conjugate base, is going to be base 1. Yes, because that goes together as a pair. Base 1. The reason I'm going this is one of my answer keys shows conjugate acid-base pairs this way. The other way to show them is to go, here is my conjugate acid-base pair. Yes? And we might call this base 2 and acid 2 because those are linked. Yeah, and another way to show that would be to show that that is a conjugate acid-base pair. The two members of a conjugate acid-base pair, where are they relative to that reaction arrow? The two members of the conjugate acid-base pair are always where relative to the arrow and relative to each other? They're always on opposite sides. Yes? That has to be true, yes, because the reason you have a conjugate acid-base pair is an acid turns into its conjugate base by proceeding through a reaction. Yes? And the base turns into its conjugate acid by proceeding through the reaction. Sorry, there's somebody bouncing their basketball in the hallway. I just want to go smack it out of their hands. I like to pretend I'm a nice person, but you know, really underneath it all, I'm just not. There was a meme recently, it's like, the moment I get behind someone, it takes only one slow walking person in the grocery store to destroy the illusion that I'm actually a nice person. I can't do it in malls, in grocery stores. There's always that person who's like walking so slowly and they've got their cart and they park it like right here. And you're like, what are you doing? You're blocking the, anyway, I'm not nice. I'm like, oh my God. I don't say anything to them, which I suppose is kind of nice, but underneath it, I'm seething. Yes, anyway. Okay. So predicting which side of an acid-base reaction is favored. Do you guys remember what it means for a side to be favored? Yeah, if a side is favored, that means those concentrations are higher. It has higher concentrations at equilibrium. So here we have an acid and a base. Who is our acid and who is our base in this HCN plus F minus? HCN is the acid and F minus is the base, and so our hydrogen is going to transfer from the acid to the base. So who are the products of this reaction? CN minus plus HF. And you'll notice I'm leaving out all the aqueuses here. I'm being a little bit lazy just so that we can, it cleans it up a little bit for just looking at this sort of stuff. Could you identify the conjugate acid-base pairs here, please? Who are the conjugate acid-base pairs? If I was to match up HCN, who would it go with? It would go with CN minus. And the F would go with HF. Now, we're going to try to identify whether the products or reactants are favored. Okay? So here we have, I'm just going to rewrite this down here, CN minus plus HF. So we are going to do this by labeling each species as either an acid or a base. And I think it's pretty straightforward to say that the ones with the H's are our acids, yes? And what am I doing? I don't even know. I don't know why I should not make them different colors. They should all be the same color. There we go. Acid, this is our base, this is our base. Now I want you to imagine this. I am HCN. Let's go and look. Who's a better acid? Let's erase all this nonsense. HCN, let's find it on our table. I think it's low down. There it is. Okay. Hydrocyanic acid. HCN. Our other acid that we are looking for is HF. Oh, there it is. So I'm just going to zoom out. You can see there are the little flowers, the little red flowers on there. This one up here is HF. This one down here is HCN. Now, over on the right-hand side, and we haven't paid much attention to these yet, are our Ka values. The Ka of HF is 3.5 times 10 to the minus 4. And the Ka of HCN is 4.9 times 10 to the minus 10. Who is the stronger acid? Even if you don't know anything about Ka values, you do know that the stronger acids are up near the top and the weaker acids are down near the bottom. So HF is the stronger weak acid and HCN is the weaker weak acid. So who is better at giving away protons? Who's better at donating protons? HF is better at donating protons. So if I am HF, okay, you're CN minus. Okay. Oh, actually, I need someone who's going to be active. Are you going to be active? Okay. So I am HF and she's HCN. Here you go. Okay. And now, because it's an equilibrium, she is going to get it back from time to time. Oh, okay, I'll take it back. But here you go. Where is the hydrogen spinning most of its time? With Anna. Yes? Because she is the weaker acid. She's not as good at giving the proton. I am better at being an acid. getting weaker when I'm my base self. I'm weaker at taking that. Like I could be like, oh, here I'm gonna try and take it. Oh, I can't do it. Oh, I finally did it. Yes? So I'm better at giving it and I'm less good at taking it. Yes, thank you so much. Thank you. So if that's the case, if we go back here, whoops, where did it go? If we go back here, and HF is the, never mind, study for your test. And we'll deal with this more next day. You'll actually be able to do some of the worksheet, the first part of it. You have enough to start on it when you're done your test. And then we'll do the rest. I answered number 52 incorrectly in each time that you can read one another. I answered it correctly on the other day. Oh. Thank you, Joanna. Yes, I will. I will be here tomorrow during flex, okay?
That's only if it was moles, I'd have to divide it by the mole.
Yeah, that's right. Yeah. Stop recording.